starting with their building blocks, namely the perceptron. So that's already a very nice name. Perceptron sounds almost like, like perception, almost like cognition. It's a good marketing name, I think. What it is really, it's a discriminative linear classifier. And it is important for our context here. It is a building block for neural networks. To represent it, we will use the so-called homogeneous coordinates. And I will say in a minute what that means. So let's say we have a feature space with two features that I call x1 tilde and x2 tilde. And we have some classifier characterized by a normal vector. And now this classifier, so let's say the one class lies on the one side of this discriminating boundary, and the other class lies on the other side. This classifier, or the decision boundary, is a set of points for which the following equation holds. So x tilde transposed w tilde. We will get rid of the tilde soon. Plus b equals 0. So b tells me how far away I am from the origin, or minus b tells me how far I am from the origin. And if I write this vector multiplication, the scalar product explicitly, I can do that as follows: x1 tilde up to xp tilde if I have a total of p dimensions, multiplied with w1 tilde up to wp tilde, plus this offset. This offset, in this particular field, people call it the bias, hence the b. And this bias can now be absorbed in an extra dimension of the parameter vector if I extend my coordinate representation by a constant 1. Okay, and this I am writing it as x transpose w equals 0. And this is now homogeneous coordinate because I don't have, because I no longer have this constant indicating the offset, the distance from the origin. And well, the only reason why we're using it here is because it will make notation a little bit lighter. Okay, now the most natural loss function perhaps for classification is simply the 0-1 loss. So to optimize the perceptron, we could use the 0-1 loss function. So I would say I want to find the parameter W which minimizes my loss. And if I use the 0, 1 loss function, I would write that as a sum over all points multiplied. I is my indicator function, so it is 1 if the argument is true and it is 0 otherwise. Okay, and here I have multiplied with the true label. So this is the label of my sample number I, and I'm here assuming that the labels are either -1 or +1. And multiplying with the label here, that's a way of abbreviating the expression by looking at the two kinds of errors that I can have, because I'm working with two classes here. So let's say if the label, if a sample belongs to class +1, I would want this product X transpose W to be larger than 0. So I want the positive class to be in the direction in which the normal vector is pointing. And otherwise, if I get a value smaller than 0, this contributes to my error. Then this expression will be true, and my indicator function will add 1 to the overall error that I wanted to minimize. Now, if I have a sample from the negative class, I want it to be the other way around. I want it to have values larger than 0, and this is why I now multiply here with yi to get two cases covered with this compact formula here. Is that clear? Am I making it too complicated? Okay. And this can be, if you don't like the indicator function, you could rewrite it in terms of a step function. So H0 is the left continuous Heaviside step function. And I have to turn it around, so that's why I'm using the minus here. So let me draw a picture for this. This is the score that my perceptron puts out. This is 0. And on the second dimension, I can plot the penalty or the loss incurred by this particular observation. And if I now predict a value larger than 0 for class +1, my penalty is 0. Or if I predict a value smaller than 0 for the negative class, that's also correct, my penalty will be 0. And if I make the wrong prediction, I incur a penalty of 1. And by left side continuous, and I've turned it around due to this minus sign here, what I was referring to is that if I predict 0, I don't give an error yet, only when I'm on the wrong side. So this value here, so at position 0, the value is 0. Okay, so we could use this function to compute an error surface, and we could use that for optimization. And I've passed a handout around, which hopefully reached the back. Here's an example data set. So we have one class and another class. I've also indicated a couple of solutions. So these three functions, by the way, are all linear classifiers that are a perfect fit to the data, in the sense that the red class is on one side and the blue class is on the other side. You might pick your preferred option among those three classifiers. Personally, I like the bold line here best. And we can, well, why do I like it best? Because it's somehow furthest away from all the samples. If the camera has sufficiently high resolution, you will see that there's still a red sample here, another red sample there, and a blue sample there. So these two extreme classifiers that I showed, they somehow, really straddle. They almost touch the two class distributions, whereas the bold one here seems to lie more stably in the middle. Okay, now for this data set, I can simply try out all classifiers. So I put in any decision function, and it need not lie in the middle. It could also be centered around here. So let's say that would be a possible decision function, that would be a possible decision function, that would be one, or that would be one. Each of these decision functions, I can parameterize them in terms of their normal vector and their bias, or in this homogeneous coordinate set, I can represent it by its three parameters, W1, W2, W3. And for each of these classifiers, I can compute the total 0, 1 error. And that's what you see plotted here. Really, I only have 2 degrees of freedom to represent such a classifier, namely slope and intercept. So I could have chosen different ways of normalizing this, but here I decided to enforce a norm of 1 for the entire parameter set, and thus represent on a sphere my energy function. And this is now the sphere unrolled. You see this is the azimuth and the elevation of my parameter vector W. Okay, and now you see that using this 0, 1 loss, this energy function, it becomes piecewise constant, and it goes from 0 up to plus 20. Why plus 20? Can you explain? It's 20 points. Exactly, it's 20 points, and they are linearly separable. So the worst I can do is put the classifier in the correct position, but oriented the wrong way around, and make a wrong prediction for each and every one. This gives me a total of 20 errors. The best error I can get is 0, if I do everything right. And thus you see altogether 20 different colors in this plot. So we have an error of 0 in the middle, and then whenever you traverse one of these contour lines, you increase your error by 1, and this goes up to a maximum of plus 20. We can make a couple of interesting observations in this plot. So we see that it is this plot here, it's piecewise constant. And by the way, these contour lines, you will perhaps guess that they are somehow related to these 20 points. And indeed, each point has exactly one contour line. We have a total of 20 contours, or 21 color levels. I think I said 20 before. It's a total of 21 color levels from 0 up to 20. That means 20 contours in between. And each of these contours is a half transform of one of the observations. Now, the half transform that is known to people from image processing, if you look at one of the observations in the original plot, you can think of all the decision functions that go through this point. Okay, so there's a whole set of decision functions that go through the point that you pick, and they will have different values for the parameters W1 up to W3. And if you trace out these different parameters, you get out exactly one of these lines that I'm showing here. So each contour line corresponds to exactly one observation. And if you traverse a contour line in this plot here, so this is the plot, remember, this is the plot of all the decision surfaces that I can possibly have. And whenever you traverse one contour here, it means that the corresponding decision surface moved across one of your points in the original feature space. Now, for optimization, this function is not so friendly because of its piecewise constant nature. So to optimize, we could use the 0,1 loss function, but the resulting energy or error surface is piecewise constant. And that means it is not amenable to gradient descent procedures. Mathematically speaking, it's perhaps even worse because the energy surface is not convex. So it has a single, in this example, or in general, for linearly separable problems, you have a single minimum, but, so I'm plotting here in some abstract picture the different parameters, and then the error surface. For linearly separable problems, we have a single minimum. But it is not convex. Convexity is the following property. If I take any point on the surface, let's say if I take any point on this function and any other point on the function, and if I draw the second, then I want for convexity to hold, the second must not cut the function in question. And for this particular second, which I've shown, the thing is true. But if I take this point here and that point, you see that the second now intersects the original function. So we do not have a convex optimization problem if we use the 0,1 loss. And the third comment is that we have this ambiguity between candidates for the optimal solution Unfortunately, we have no single candidate for linearly separable problems like the one you've seen here. So let me show this picture again here. This minimum energy region, the one where the error is 0, it has some finite extent. So there are many classifiers that are a good fit to your, or that are a perfect fit to your training data. And I have shown 3 of these classifiers up there. By the way, could you try and relate these 3 classifiers to different corners of my minimum energy region? So could you tell me qualitatively what is happening? So I don't expect you to show me the exact coordinates because especially because I've not given the coordinate system in the feature plot. But you can note that one classifier touches one class and another one touches 2 classes. The other one touches none of the 2 classes. How can you relate that to this, to positions in this minimum energy region? Go ahead. Yes. So I'm trying to show a blow up here of this minimum energy region. I haven't understood that. Can somebody else explain it in a different way? I'm not saying it's wrong, I just haven't understood it. Go ahead.
I think that the bold line is just right in the middle of the minimum region.
Mm-hmm.
And the closer you get to touching a point with your decision boundary, the closer you get to one of these contours. And as we cut through 3 points with one of the lines, we should be touching 3 contours for one of the decision boundary points.
Yes, that's correct.
And the other one we should touch 2 contours. And by, for example, if we take a look at the one that touches 3 points, there's 2 points of one class and one of the other, so there should be 2 contours that are fairly equal, and another one that's shifted by.
Yeah. So, sorry, the plot is too dark here for you to say any details, but very roughly, the energy minimum, so the area of 0, the region of 0 error, it looked roughly triangular. If you look in close detail, it's not fully triangular, but something like it. And this classifier here, it touches both the blue class and the red class. So that's a classifier which could perhaps, so let's say this one, it could perhaps reside here, yeah, in this very corner. It's an extreme case. It's the very limit of this space of feasible solutions. This classifier here, it touches just the one class in 2 points actually. So yes, it should meet 2 contour lines, but it will not be so close to a corner of the triangle. So these 2 points will be represented by lines that are almost parallel, and it will meet or it will intersect these lines, perhaps here. So we're on the side of this, actually it's called the version space. And indeed, my favorite solution here sits smack in the middle of this space of all allowed solutions. And again, this minimum energy region is called the version space. And there are now different ways, and this is now coming very close to present-day research, on what is the best spot, or what is in some ways the most robust classifier, which point of version space should you pick. And you could simply pick the point that has the largest distance from all sides, or you could pick a point that you can take entropy criteria into account and so on, or you could compute the center of mass. So there are different ways of defining what is the center of version space. But the methods that we look at next week, support vector machines, they are much more interested in getting to a center of version space, whereas the perceptron, if you use the 0-1 error, it knows nothing about it. It just knows my error is minimal or not minimal, but the perceptron in itself, it could not discriminate between these different solutions here. However, given a test set, you can of course still find out which one is better. All right. So we see that the 0-1 error, it has, in some ways it's a natural thing to do, but for optimization, it's an unfriendly quantity because of this piecewise constant nature, and because of the ambiguity of the minimum and so on. And that's why you can use a smoother error function instead. So here I showed a very hard penalty, and you could now start to mellow this out. So you could, for instance, use a smoothed version thereof. And indeed, if I use a smoothed version as shown, I get a plot like you see at the very bottom. This problem actually is still not convex, as you can perhaps imagine. So if you if you imagine it as a 3D plot, if you draw a secant from this point to the minimum, you will cut through the surface, so it's still not convex, but now at least you can use gradient descent procedures if you like. So one can use smoother or smoothed error functions instead. And that will leave the non-convexity, but it can help with this ambiguity, and it can help by allowing the use of gradient descent procedures. if you could switch the camera, Bernhard. So I here show an example which is no longer linearly separable, and there are actually now two distinct minima in this error surface. There's one here and one there, and if you look more closely you find two more. Roughly these minima correspond to this solution or to that solution. And if you now start smoothing this error function a little bit, you will not get rid of those local minima. And even though we're just looking at a single perceptron here, this is already a bad foreboding, or this already illustrates a property that we will still encounter if we now combine many of them together to obtain a neural network. So if we use smoother functions, we now have gradient descent that's possible. We still have a non-convex error function, and depending on how much you smooth, you may lift the ambiguity of local minima. So let's look at what a gradient descent procedure could look like. So gradient descent training. We now introduce an artificial time parameter, and we'll say that our parameter vector at time +1 is given by the old parameter vector minus some magic step size, which in itself is often a function of time. So this is typically something that decreases over time. And then the derivative of this error function with respect to its parameters. Now this is a general formula that I've written down, and the one that is traditionally used for the perceptron is the following. So we now sum only over the misclassified samples. So those that were misclassified at time step t. And if it was a sample of the positive class, then we simply add mu times it to our current parameter estimate. And if it was a sample of the negative class, then we subtract mu times the position of that sample from the parameter vector. Again, the only admissible labels here, or I'm assuming that the following coding for the labels has been used, -1 or +1. Now you can ask yourself, what error function does this traditional perceptron optimization rule correspond to? And you can find it out by integrating. So we know that this is a derivative with respect to W. So if I want to know the original energy function, I need to integrate with respect to W. And I can then find that this corresponds to the following energy function. And back in those days, it wasn't called that way, but today people have a name for it, and now they call this the central hinge loss. So hinge is a Scharnier, like wie eine Tür, and I will explain this term in a moment. So by writing hinge, I don't say anything. This is an abbreviation, but a compact way to write it is the following. It is the maximum of either the argument or 0. And the plot will explain this a lot better. So here is the score, the output of my perceptron. And again, the 0-1 loss looked like that. That was the 0-1 loss. And I can now use different color to show the nature of the hinge loss. So it's 0 for correct predictions, and the penalty that you incur grows linearly with your distance from the decision boundary. If you made something, if you had an error in your prediction. So the green line here is the central hinge loss. And by the way, support vector machines are all about the hinge loss, but no longer the central one, but a shifted version. We will talk about that at length next week. So for an SVM, you would have that. That would be the SVM type, the support vector machine type hinge loss. And the big difference here is that with the central hinge loss, with the green line, you start giving a penalty as long as you made an error. With the SVM type hinge, you already give an error if an observation, even if correctly classified, only dares to come close to the decision boundary. So it's even more cautious. And this helps pushing the decision boundary away from all samples, and this helps you find a solution in the center of version space rather than at its very limits. Okay, but back in those days it was not yet called hinge loss, it was called the perceptron learning algorithm, and you can use this recipe here for either batch learning or online learning. The way I wrote it here, so to go from time step or from epoch t to training epoch t+1, I summed over the contributions from all training samples. So this is why this amounted to a batch learning process. So you can either do batch learning, all samples at once, or you can do online learning. Or if you want a fancier name, stochastic gradient descent. In stochastic gradient descent, you do not sum up your contributions from all samples, but you collect the contributions from your samples one by one and then re-evaluate your loss function. And it turns out that this online learning or stochastic gradient descent is actually empirically, this is better for neural networks, even though it gives you an order dependence. So you essentially inject an element of randomness into your optimization procedure, which helps. By order dependence, I mean that the results will differ. You may end up in different local minima depending on the order in which you presented your training samples. Okay. Any questions about the perceptron? Go ahead.
About the neural networks, we said about the perceptron that it's a linear classifier. So do we assume for any artificial neural network that we linear classifier?
So after the break, we will see how to combine multiple perceptrons into a neural network. And that can then implement nonlinear decision boundaries. More questions on the perceptron? Okay, so in batch learning, the difference between batch and online learning. In batch learning, let's say I have 1,000 samples in my training set. In batch learning, you sum up your contributions from all your 1,000 samples and then update your parameter vector. In online learning, you process just a single sample, at which point you adjust your normal vector. And now that you have adjusted your normal vector, the set of what you classified right and wrong is no longer the same. And then you process the next wrongly predicted sample. So it's not identical because, you see, this is a set of points. The sum of the set of misclassified points, and which points are misclassified changes each time that you update your parameter vector. And this is why one point at a time, exactly. For all points. And then exactly. You always pick a single point from the misclassified set. Or in fact, you pick points randomly until you find the first one which is misclassified, and that one you use to update your parameter vector, and so on. And you see, for linearly separable problems, the problem is not convex, but it has a unique minimum plateau, even if within this unique minimum plateau you don't have a unique optimum solution. So for linearly separable problems, whatever you do, anyway, this procedure only works when you use hinge loss, for which the gradient exists at most points. So if you use the hinge loss on a single perceptron in a data set, no matter whether linearly separable or not, this actually does give you convexity. You can already study it here in these functions. So the brown one is not convex, because if I connect, let's say, this point with that point, I cut my step function, right? Because my step function, you see the brown and the red line, they intersect. However, both the non-central and the central loss functions, they actually are both convex. So if I pick any point here on the purple line and any other point on the purple line, it will never intersect the purple line. It can at most be parallel to the purple line. So the hinge loss gives you a convex error surface. And that means up to the ambiguity of the minimum, there will only be one minimum energy region. And that you will certainly find no matter if you do batch or online learning. The difference really comes when you now combine multiple neural networks into multiple perceptrons into a neural network, because when you do so, as you will see after the break, you use a nonlinear activation function in each of the perceptrons, and that destroys the convexity. And then you can have multiple distinct local minima, and then it really matters, or that you can really get different results if you use batch or online learning. Okay, so the big difference between batch and online learning only happens in neural networks, not in perceptrons. But I wanted to mention it already here because we're now talking about gradient and gradient descent. More comments? Okay, we have a break and then talk about the networks themselves. I've thought of one more thing to say. Because we were talking about optimization so much, and one way to optimize it is exactly, namely in terms of linear program, I can minimize the following. I can say my optimum parameters will be given by the following. And this is for all I. And these xi's, they are the so-called slack variables. So normally I would say that, at least for linearly separable problems, I'm looking for a solution W such that yi xi transpose W is larger than or equal to 0 for all observations. And now I'm relaxing this constraint. I'm saying it need not be 0. It can be greater than or equal 0 up to a slack xi I. And these slack variables should be constant. And then I want to minimize the sum of these slack variables. So for a linearly separable problem, the sum of the slack variables will be exactly 0. And W will be one of the possible W's from version space. There will typically not be a unique solution. And you see we have a linear objective function. It's linear in the slack variables, and we have linear constraints, and that makes the whole thing a linear program. And well, perceptrons are not usually optimized in that way. I think it's perhaps mainly a traditional reason, because back in the days it was hard enough to compute the gradient, and computing a linear program is even more expensive. But this will give you the solution in one step without any iterations and so on. And we're going to see very similar formula next week when we talk about the support vector machine. It is harder, but it has the advantage of being in a standard form, which standard optimization packages will understand. But yes, indeed, you introduced these auxiliary variables.